Unit 2.3, specific heat and latent heat. Specific heat is the amount of energy needed to raise 1 kilogram of a substance by 1 degree Celsius. Now remember that 1 degree Celsius equals 1 Kelvin. The scales are the size of a degree in the two scales are equivalent. The symbol is C, and the units are joules per kilogram Kelvin. You can also find this in all sorts of different kinds of units, but that's what we'll be using in our assignments. A calorimeter can be used to determine the heat lost or gained. A calorimeter is basically just an insulated container, like a thermos. Here's an example. 0.05 kilograms of a sample of an ideal gas is heated to 100 degrees Celsius from 42 degrees Celsius. What is the heat gained by the gas if the specific heat is 650 joules per kilogram Kelvin? Okay, so what I'm going to do is identify my variables. First of all, I know that the mass is 0.0500 kilograms. Next, I know the initial temperature is 100 degrees Celsius. The final temperature is 42 degrees Celsius, which means that the change in temperature is final minus initial, which is 42 minus 100, which is negative 58. Okay, and then I've got the specific heat is 650 joules per kilogram Kelvin. So this is a pretty straightforward plug it in and solve it question. So Q, the heat lost or gained, is equal to the mass times the specific heat times the change in temperature. And actually, you know, when I look at this, what I realize, I'm going to fix this. I wrote this for water, so my apologies. Because really you can apply it to anything, any substance. So Q will equal the mass, that's 0.05, times the specific, 0.05 kilograms. I'll leave the units on there to make a point. So the specific heat, which is 650 joules per kilogram Kelvin, and then times a temperature change of negative 58 Kelvin. So look what's going to happen here. One of the things I love about specific heat is we can see the units cancel. We're going to be left with joules. And now I just need to do the arithmetic. So 0.05 times 650 times 58, negative 58. And I get that the change is negative 1,885 joules. There's my change in heat. So the gas lost heat. It lost that much energy and its temperature changed. So heat and temperature are related, but they're not quite the same thing. Okay, next we're going to review latent heat, otherwise known as heats of fusion and vaporization. So here's my question. What happens to the temperature of water during boiling? The temperature actually remains constant. Why is this? It's because the energy added is used to overcome the attractive forces so that the average kinetic energy of the molecules doesn't increase and the temperature stays constant. In other words, the energy goes into the phase change instead of the temperature change. It goes into changing the nature of the substance from solid to liquid or from liquid to gas. When we go between solid and liquid, that is the heat of fusion. When we go between liquid and gas, that is the heat of vaporization. And that's what I've got written here. Heat of fusion is solid-liquid phase change, and vaporization is liquid-gas change. And with latent heat or heat of fusion and vaporization, the formula looks similar to specific heat, but not quite the same. It's actually a little bit simpler. Instead of Q equals MC delta T, all you need is the mass times the latent heat. The latent heat will be measured in joules per kilogram, and it's specific to the substance itself. So just a reminder of one of these energy graphs. If we have, let's say we have water, which is kind of our go-to because we're familiar with it. If I've got an ice cube that is at, say, negative 10 degrees Celsius, it's going to be ice. And before I can melt that ice cube, I have to bring it up to the melting point. And for water, that melting point would be 0 degrees Celsius. Then when it's converting from solid to liquid, the temperature does not change. It remains at 0 degrees Celsius. Once it converts into liquid, icy, well, maybe I shouldn't call it icy water, 0 degree Celsius water, now I can raise its temperature again until I get to the point where the water will boil. And we know that that point is 100 degrees Celsius. Then we add more energy, and that energy again goes into the phase change from liquid to gas. And you'll notice that this is actually a much wider span for water. It takes a lot of energy to convert water into steam, and steam holds a lot of energy, which is why it's really useful in cleaning, among other things. Anyway, once we turn the water into water vapor, then we can heat it up again in its gas state. You'll notice also, one thing that I wanted to make sure to mention, by the way, is that, let's see, down here we've got the heat of fusion. The heat of fusion, again, is going to be the heat it takes to change something from solid to liquid or vice versa. And then the heat of vaporization, that value, the amount of energy it takes to change the water from liquid to gas. Again, this is just for water, is 2,258 joules per gram of water. I've also written down the specific heats of different forms of water vapor, liquid water, and ice. Okay, so let's do an example here. Find the energy required to turn ice at negative 10 degrees Celsius into steam. So first, I have to warm the ice to 0 degrees. So my initial temperature would be negative 10, and my final temperature during this portion of the experiment would be 0. The specific heat of ice is 2,093 joules per kilogram Kelvin. And this reminds me that I need to have an amount here. I haven't given myself an amount in this example, so let's do it. Let's say the mass is 1 kilogram, just to keep things simple. Okay, so the amount of energy needed to warm 1 kilogram of ice from negative 10 to 0 degrees, I'm going to use the specific heat equation. The mass is 1 kilogram. The specific heat is 2,093 joules per kilogram Kelvin. And the change, the final minus the initial, is going to be 0 minus negative 10. So that's 10. So when I multiply that out, I'm going to get 20,930 joules. Okay. Then I have to change the ice to water, and that's a phase change. And when I do a phase change, that's going to be my latent heat. So latent heat, the heat required to do a phase change is just M, the mass, times the heat of fusion. And the mass of the substance is just 1 kilogram. It's the same amount of stuff, same amount of water. And the heat of fusion for that water is 334 kilojoules. So that's 334,000 joules per kilogram. And when I multiply that out, I'm going to get 334,000 joules. Okay. And now I have to heat that water. To get it to steam, I'm going to have to heat it up to 100 degrees. And let's see, my initial temperature is 0 degrees Celsius and my final temperature is 100 degrees Celsius. So I'm going to do the same type of thing as before. Q equals MC delta T. So Q equals the 1 kilogram. Okay, now the specific heat for water is 4,186 joules per kilogram per Kelvin. And the temperature change, the final minus the initial, is going to be 100 minus 0, or 100. And now I'm going to multiply this out, and I'm going to get 418600 joules. Okay, and finally, I have to actually do the phase change. Who knew water was doing all this work? From water to steam or water vapor. I guess it's actually water vapor, isn't it? My chem is a little rusty. So again, Q equals MH. M is still 1 kilogram, but now I need the latent heat of vaporization, and that's 2,258. That's joules per gram. So actually, well, if I should have done a better job and given you I should have given it to you in kilograms, but I also could do this. 1 kilogram is 1,000 grams, and I can multiply that by 2093 joules per gram, and when I multiply that out, I get 2093000. Okay, so to answer the question now of how much energy does it take, I have to add all 4 of these things up. So 20,930 plus 334,000 plus 418,000 plus 2,093,000. And notice again that the phase change from water to steam is where most of the energy is. And when I add all of this together, I get 2,865,000 joules of energy required to take 1 kilogram of ice. That's basically a liter of ice, like half a 2-liter bottle, from negative 10 degrees Celsius up to steam or water vapor.